So today we move into a new chapter, chapter 12. It deals with ideal gas mixtures. There's really two big parts to this chapter. One is any ideal gas mixture, and then we're going to be able to, once we describe how to calculate properties of gas mixtures, then what we're going to do is use it to solve problems. We'll do closed system process type of calculations as well as open system calculations. Then the second half is very different from the first half, but we use all the tools built up in the first half, and we analyze a specific mixture of great interest to mechanical engineers, and that's moist air, where we have water vapor behaving as an ideal gas, and then dry air. So we only consider it like a binary. I know that dry air is made up of nitrogen, oxygen, carbon dioxide, and other elements, but we just lump it and call it dry air. And then when you have water vapor in it, it's now moist air. And it makes people uncomfortable. It has a big impact on manufacturing processes, etc. So that's the second half of the chapter. So we are experts in ideal gas equation. Okay, you write it like this: PV is equal to nRT. We have to understand each term in the equation. Isn't this the absolute pressure and the absolute temperature? Isn't this the volume, the number of moles? And then I messed up. I need to put a bar on that, don't I? Isn't that the R bar, which is the universal gas constant? Yeah. And then you can write it by bringing this N over here, and you have PV over N divided equal to R bar T. But what is cap V divided by N? Isn't that V bar? All right, well, what is V bar? That's our volume per amount. That, just look at the units on it. It's meter cubed per kilomole. So the textbook uses this bar on top of the R. Oh, that's to denote that it's per a mole or kilomole. Just like this bar on top of the V. It's not per unit mass. Well, you can also put PV is equal to mRT. That's a mass description. M is the number of kilograms. And R, how is R and R bar related? R is equal to R bar divided by big M. What's big M? Molar mass. And then if you put PV divided by M is equal to RT, what is this term? The specific volume. And so right away I have four versions of the ideal gas equation. We need to be familiar with all of them. And then another version is we say P is equal to 1 over V RT. You say the reciprocal of the specific volume, what is that? Mass density. And so this one we really haven't used a lot in Thermo 1 or Thermo 2, but it's actually used a lot out there in practice because people like to talk about mass density in preference to specific volume. I think more people have an intuition about mass density, and so this is a very favorite form of the equation. All right. Molar mass, big M. What are the units on big M? Right here. Who's next? A. It's kilograms per kilomole. Previously, we talked about how much mass there was and how many moles there are. Isn't it the ratio of M to N? Yeah. Isn't that what it is? And so now I could go back and forth between a mass description and a molar description. So maybe I'm given M and I want to know how many moles it is. What would I do? Wouldn't I divide by cap M? Or if I'm given the number of moles and I want to know how much mass it is, wouldn't I multiply by cap M, the molar mass? How many people remember learning the name of the molar mass as called the molecular weight? Yeah, still, I don't know why it's still taught that way, right? but in the textbooks in high school and physics classes, they still call it the molecular weight. I learned it that way, but I try to call it the molar mass because it's a little cleaner what exactly it is. Okay. All right, what is the relationship between a mole and a kilomole? We prefer to work as mechanical engineers in kilomoles, just because that's what it is. And then you go to the scientists, everything's grams and everything's moles. So answer A is correct or answer B? B. We have a vote for B. 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 You're fast to get an answer in on this one. Hey, professor. Now we're going to talk about a mole fraction and a molar analysis of a gas. So the book will use a subscript on an N, call it N1 or N2 or N3. That means that you have like component 1 in the gas. Maybe 1 stands for the nitrogen, maybe 2 stands for oxygen, maybe 3 subscript stands for the carbon dioxide, or maybe we write it out. But in general, you have multiple components that make up a mixture. Now, what does N without a subscript in this textbook stand for? The total number of moles in the mixture, ideal gas mixture. So does this equation make sense? I may have 5 kilomoles of this, 7 kilomoles of that, 13 kilomoles of this. I add them all together and I have whatever I had. What did I think? I got 15 kilomoles total for that example. All right. Now, if you take that equation, which makes sense and is true, and you divide each term by n, the left-hand side is trivial. It just becomes 1, doesn't it? And then you have n1 divided by the total number of n, n2 divided by the total number, n3 divided by the total number, etc., how many components you have. And this is defined as y1. And that's y2, and that's y3. Those y's are simply the amount of that particular species of interest, maybe put a subscript I on there, divided by the total amount. It's the mole fraction. It's a mole fraction. So it adds up to 100%. Maybe I have 20% nitrogen, 70% this and 10% that. They all add up to 100%. It's mole fraction. Okay? All right. Well, you could do a molar analysis and talk about the mole fractions. You can do a mass analysis and talk about the mass fractions. So the same concept, we say we have the total mass of the mixture. Oh, there's so many kilograms of this species, so many kilograms of this species, so kilograms of that species, etc. Take both sides of the equation, divide by m. We get 100% is equal to m1 divided by the total mass, m2 divided by the total mass, m3 divided by the total mass. And at this point, the symbol that they use for the mass fraction is different in some textbooks. This textbook, one of the earlier editions way back when, they used X. Do you think that was a good choice? X? Because you get confused. No. So I don't remember when they changed it, or at least I remember I learned it as X somewhere in my life in different textbooks. Okay, I don't prefer X. I don't like X for mass fraction. Okay, so you're maybe the author of the textbook and you're thinking, well, we've used X, we used Y, how about Z? Gravity, elevation, maybe not. I don't know. What do you want? So they keep going. Okay, fine, we run out. Let's go to the Greek letters. No, let's stay away from the Greek letters, right? That's usually what happens when they figure out. Anyway, they put this MF, 2 letters. And then we put a subscript 1, the mass fraction, subscript 2, the mass fraction, subscript 3. So there you go. That's what they use for the mass fraction in this textbook. I prefer that. It's less confusing. Easy to remember. Okay. We have 2 models of ideal gas mixture, Amagat's and Dalton's model. One gives us the partial volume concept, one gives us the partial pressure concept. So the partial volume concept is like this. I have a total volume. It's made up of just two components. And if you could conceptually separate it such that this volume plus that volume gives me the total volume, and all that's in the first volume would be all of the first gas. Let's say it's colored red to try and distinguish it from the blue. Okay, maybe this one's the oxygen and maybe this one's the nitrogen or something. Just think of it as examples. And that's our partial volume concept. So you can start with this equation, V is equal to V1 plus V2. And if somebody said, what's the volume fraction? You would say V divided by V, that's 100%. It's equal to V1 divided by total V plus V2 divided by total V. So this is our volume fraction. And that's our volume fraction for the second component. Well, the volume fraction V1 divided by V is equal to, let's apply the ideal gas law. So P V is equal to N R bar T. They behave as ideal gases always. So for the first component right here, these have the same pressure and the temperature. You're not changing the pressure and the temperature. All you're doing is pushing every one of the N1 into V1. That makes sense? So what you could do is you could replace V1 by, here, V1 is equal to N1 R bar T over P. You can replace that right here. So N1 R bar T over P. Likewise, for V, for the total, PV is equal to nRT with a bar on it. Then you can replace V by N R bar T over P. Let's cancel the R bars, the T, the P. And so the volume fraction, V1 over V, is equal to N1 over N, which is Y1. What was Y1? Mole fraction. So the mole fraction and the volume fraction are the same for ideal gas mixtures. So somebody can come in and say, here is my analysis of a gas. I have 20% is oxygen and 80% is nitrogen. You say, is that a mole fraction? Are you giving me mole fractions? Is that what the 20% means? Is this Y of O2 is equal to 0.2 and Y of N2 is equal to 0.8? They say yes. Then you know what? I know the volume fraction for that ideal gas. The volume occupied by the oxygen is 80%, and the volume occupied by the nitrogen is, did I mess that up? Oxygen is 20 and nitrogen is 80%. Okay. Dalton's law. You're very familiar with it, I believe. The concept of partial pressures. Here, what you do is you leave the volume the same. The volume and the temperature are unchanged. But what happens is the pressure. You have the total gas pressure, and then you'll have this partial pressure as if the whole volume is occupied only by the one gas. And then the other one is the partial pressure. It's as if the total volume is occupied by just the second gas. I only have two gases in this illustration. So these are partial pressures. Okay. We have an equation that says that the partial pressure of a gas is equal to the mole fraction of that gas times the total gas pressure. Well, where did that come from? Well, we use this equation a lot. The partial pressure of that component is equal to the mole fraction of that component times the total gas pressure. Okay. Well, let's do this. Let's write PI. Let's do this. Write the ideal gas law. PV is equal to nRT, R bar T. And now for Dalton's model, we're going to put the partial pressure, PI, V is equal to NIRT. So you can write that equation two times. PV is equal to NR bar T, and then with the partial partial pressure I, PI, and the number of moles I. Okay. So you say PI is equal to NI R bar T over V. Just using this equation right here, right? And then you use this equation and you say what is R bar T over V? That's equal to P over N. Is that true? So I can come down here and say this R bar T over V can be replaced by, I got Ni, I got P over N. Hey, what is this N sub I divided by N? Mole fraction. It's almost like explaining something that's so obvious, but there it is. I tried to explain it or show it or demonstrate it so that this equation is true. And that's very common that we use this concept of partial pressures and the mole fraction, multiply the total pressure by the mole fraction to get us the partial pressure. All right, let's start solving some problems. A molar analysis of a gas mixture is 15% nitrogen, 20% carbon dioxide, and 65% methane. All right. The gas pressure is 240 kilopascal and the temperature is given. Determine the mixture molar mass, and there's the answer. How would you get the mixture molar mass? Well, the mixture molar mass is equal to the total mass of the mixture divided by the number of moles of the mixture. I would start and say pick or assume that the total number of moles of the mixture is 1 kilomole. And I think that's a starting point that's a little hard to get started at. But as soon as somebody says, you know what, start there, make that assumption and run with it, then I think it's easy to do this analysis. I think it's easy to set it up like an Excel spreadsheet, a little table. So you would say, how many species do I have? Nitrogen, carbon dioxide, CH4. Hey, did I ask you what the name of CH4 is? You know, I look at this N2 and I say, oh, nitrogen. I look at this CO2, oh, carbon dioxide. I look at CH4. Methane. You're the man. Very good. Methane. So there it is. We probably are going to need to know the molar mass in kilograms per kilomole. So where in our textbook do we get the molar mass of nitrogen, carbon dioxide, and methane? Table A1. Table A1, the first table. And nitrogen, let me look it up here, is 28.01, good to 4 digits. Carbon dioxide, 44.01, and then 16.04. Notice which one has the lowest molar mass? The methane. It's the smallest. It's the least heavy or the least massive molecule, gas molecule. Which one is the highest molar mass? Carbon dioxide. It's large, heavy, massive compared to the other ones in this analysis. Okay, you're given the Y's, the mole fractions. So what was it for this problem? 15, 0.15, 0.20, and 0.65. If you pick that n is equal to 1, can you now calculate? This is almost too trivial. Can you tell me how many kilomoles there are of each of the species? Isn't Ni equal to Yi times N? And so I know this is funny, but this is dimensionless on the Y. This is how many kilomoles I have. And so I have 0.15 kilomole. I have 0.20 kilomole, 0.65 kilomole. Now that I know how many kilomoles I have, I multiply that by the molar mass to get M in kilograms, don't I? Yeah. So 0.15 times 28.01, I believe that comes in at 4.2015 kilograms. And then the next is 8.802 kilograms, and then 10.406 kilograms. All right, I add those three up, and what does it give me? 23.4295. Now we look at that number for a minute and we think, that is how much mass I have with the pick or the assumption or the starting point of 1 kilomole of the mixture. That's my molar mass. The molar mass is 23.43. Again, it's how many kilograms per kilomole. You kind of picked the number of kilomoles to be 1 to start the process off. All right. Let's continue on. You ready to continue on? What I'm going to do is I'm going to copy this table right here because I think I'm going to build on it in a second. We have the same mixture, the same problem. Part B, though, we're continuing. Perform a gravimetric analysis of the mixture. All right. We had a molar analysis, which is equivalent to a volume analysis. That's the way we started. But now they're asking me the gravimetric analysis. It's like gravity, doesn't that indicate weights? But the gravimetric analysis is equivalent to the what analysis, just like the molar analysis was equivalent to a volume analysis. It's a mass. Yeah, mass fractions. Exactly right. The answer that they're looking for are the mass fractions. So don't let this word gravimetric throw you off. It's in the book. It's in the lecture. Fair game on final exams. All right, so what we're going to do is we're going to do a paste here, there. And we just continue this table over, don't we? So we started with the assumption of 1 mole, and then we continue on the process. So if I'm looking to calculate the mass fraction for each component, which is dimensionless, just like the mole fraction was dimensionless, how do I calculate? Isn't it 4.2015 divided by 23.4295? Isn't that it? Yeah, so you just take this number, divide it by that number, and you have the mass fraction for the nitrogen, which comes in at 0.179, about 18%. And then the same here, it's 8.802 divided by 23.4295, comes in at 37.6%. And the same, it's 44.5%. Let's put this one as a percentage. 17.9%. Let's do a little comparison. It was 65% on a molar basis, but now it's only about 45%. Why? Why the change? Why the reduction? Because it's a light molecule. It's very light. It has a low molar mass. Right. Okay, very good. Okay, let's go to part C. What is the partial pressure of the carbon dioxide? Yep. And so you're going to get that the Y of the carbon dioxide, that mole fraction, times that total gas pressure, which is 240. So we didn't use mass fractions, did we? We used the mole fraction, which is right up here, 20%. So is 0.20 times 240? Is that equal to 48 kilopascal? Very good. You can get the partial pressures of all of the components, but there we just ask for one. Next question. What is the volume occupied by 1.8 kilomoles of that mixture? How would you do that one? Just use the ideal gas equation. Let's see. I have a pressure, total pressure of the mixture. I have the volume of the mixture. That's what I'm asked to calculate. I have the number of moles of the mixture. Guess what? That was given, isn't it? 1.8 kilomoles. And then I could put R bar there and then the absolute temperature. So V is equal to N R bar T divided by P. So 1.8 kilomole. R bar is 8.314 kilojoules per kilomole Kelvin, but 1 kilojoule is precisely 1 kilopascal times 1 meter cubed. So a lot of times R bar, I don't like to put kilojoule there because I want pressure and volume. So I'll put kilopascal meter cubed there. And then we multiply by the temperature, 330 Kelvin, and divide by the pressure in kilopascal, 240, and there you go. Did it really matter that it was so much nitrogen, so much carbon dioxide, so much methane? Could have been 100% methane, and would, at the same pressure and temperature, would it have been the same volume? That's an interesting question, isn't it? Yeah, if it would have been 100% CH4 and nothing carbon, nothing nitrogen, you'd have the same volume because they all behave as an ideal gas. Right? All right. Let's press on. Another part, part E. Okay. Partial volume of the nitrogen in meter cubed in 1.8 kilomoles of that mixture. So we know that the total volume occupied by 1.8 kilomoles is that volume. So how do I calculate that partial volume? How do I calculate the volume occupied by the nitrogen? It's the Amigat's model, the partial volume concept. Yep. So the mole fraction of the nitrogen is equal to, let me write it over here, the mole fraction of the nitrogen, which is defined as the amount of nitrogen divided by the total number of moles of the mixture, is equal to the volume, the partial volume concept of the nitrogen divided by the total volume. Volume fractions and mole fractions are equivalent in ideal gas mixtures. So you just multiply the mole fraction times total volume. So what was our mole fraction for the nitrogen? 0.15 times 20.577 meter cubed, and you'll get 3.087 meter cubed. There are other ways to solve it, but that one's a pretty fast way. Okay? Thank you. I forgot to say thank you, huh? Press on. Okay. Volume occupied if you had 62 kilograms of the mixture. How would you calculate that volume if somebody said, yes, sir? Ideal gas equation? Yep. And so what you could do is you have PV is equal to M, R, which is R bar divided by the molar mass, times T. Okay? And so you're given that this is 62 kilograms. You already know the molar mass. Yep. Or another way to think of it is calculate N, how many moles. So I have the mass divided by the molar mass. I really get back to how many moles of the gas I have. Once I have the kilomoles, then it's just like the previous problem. So it comes in about 30.25 meter cubed. There are some of the numbers worked out in Excel, but we just worked them out and showed them to you, okay? It's easy to build these in the table. All right. As we continue, we're interested in solving thermodynamic, conservation of energy, first law or second law problems for systems that maybe a closed system undergoes a process or an open system where we have in and out flow. Well, we're going to have to calculate changes in properties. Maybe changes in internal energy. Maybe next slide changes in H, and maybe the next slide changes in entropy. How do you calculate the change of cap U for an ideal gas mixture? Well, if it was made up of only one component, it'd be really easy. You would say, well, it would just be that mass of that component times U2 minus U1. All right, but if we have multiple components, then we have to do a summation over each of those components. That's all it is. So on a mass basis, you just do it like you would do it for the single component. All right, how about on a molar basis? Well, you would say how many moles of that species times U2 minus U1, but I put a bar on those U's. What does the bar indicate on that lowercase u? It's now on a per unit kilomole basis instead of internal energy on a per unit mass basis or per kilogram. So this is a molar analysis or a mass analysis. You can solve a lot of problems either, okay, I'm going to go with a molar analysis or a mass analysis. I'm going to be looking at mole fractions or mass fractions, etc. All right. Somebody says, I have a constant specific heats. How does that modify our equation? Well, we would say that C sub V times T2 minus T1, isn't that equal to the change in U? Sure. And so you would have the mass of that species, the specific heat constant volume of that species, and then the temperature change 1 to 2 of that species. Most of the time, the mixture, you have to be careful. There's not a partial temperature concept. We'll solve a problem where we struggle with exactly, this is the final temperature of that component, this is the initial temperature of that component, and you just have to go slowly. We do not have a partial temperature concept, but the components could start at different temperatures and end at the same temperature. That's very common. Mixing until you get to thermal equilibrium. How about over here? Do we have an equivalent equation for the molar? Do I have N sub I, C sub V sub I, T2 minus T1I? Only thing I need to do is put a bar on that CV. Does it make sense to have a bar on top of the CV? Sure, it does. And so this specific heat, just look at the units, kilojoules per kilogram Kelvin. The units on this CV are kilojoules per kilomole Kelvin. Somebody says, hey, I don't know C sub V bar for nitrogen. Okay. But I know C sub V for the nitrogen on a mass basis. I think I can either multiply by the molar mass or divide by the molar mass, one of the two, and I can get C sub V bar for the molar mass of the nitrogen. Which one would you do? Would you multiply or divide by the molar mass of nitrogen? Multiply? Multiply? Anybody else? Multiply? Yeah. And how did you determine that so fast? You looked at your equation sheet real fast? No, they did it a little faster without looking at an equation sheet. How'd you do it so fast? You did look at the analysis of the units. That's right. And so right away you're remembering these units, kilojoules per kilogram Kelvin, and you remember, oh, molar mass is kilogram per kilomole. When the kilograms go, kilojoules per kilomole Kelvin, I'm happy on the units. And the reciprocal would not have worked. Dividing by molar mass would not have worked. Okay. Okay. So, what do you think is when you have the change in enthalpy? Somebody comes and they say, now it's H2 minus H1. What do you think? The whole slide basically is repeated, where instead of the lowercase u, you have the lowercase h, or the lowercase h bar. And then instead of the CV, what do we have? CP. The CP. All right? Likewise. So it's easy. Okay, once I understand change in internal energy, the change in enthalpy is easy. Okay. Little harder here. All right. So we're going to be interested in calculating the change in entropy of our ideal gas mixture. We'll do it both on a mass basis as well as a molar basis. All right. Mass basis. Let's see if we can work that one out. If I just had one component, I would get the mass of that component, and then I would get S2 minus S1 for that component. How did I calculate it for ideal gases? Wasn't it something like S2 naught minus S1 naught minus R times natural log of P2 over P1? How many people remember this equation? Yeah. Okay. Refresh my memory a little bit. Was the S naughts, are they a function of temperature only? Yeah. And then what is this P over here in this equation? It's your pressure, and it's a ratio of pressures. And you can take the natural log of a ratio of pressures. So this is bringing back good warm memories that we had of making these calculations before. Okay, what was the naught on this S indicating? Low pressure, low pressure, low pressure. And it's like these are at the same low pressure, and this accounts for the change in pressure, the pressure effects on the entropy. Okay, all right. Now, if you had multiple components, wouldn't you just do a sum over each component? And then I have to come in here and I have to say the S2I, the S1I, this R, I don't know if there's a subscript. Is there an RI? I don't think so. But if it's R is equal to R bar divided by the molar mass, then yeah, I need to maybe I should do that way. Put R bar divided by the molar mass, and then it is for that component I. Okay. And then I have this natural log of P2. This is where I need to be careful. I need to put a P2I and a P1I. And that'll take a little bit of work, and I'm going to solve a problem where I have to work through that. Okay? So it's like initial state 1. I need to find the pressure or the partial pressure of that component. If it's already in a gas mixture, it's a partial pressure. If it's a pure state, then it's the pressure because it's pure. It's 100% by itself. The mole fraction is 100%. And then likewise, typically it's a mixing process at the end, state 2. P2I is the partial pressure of that component in that final mixture. Okay. All right. Let's go over here to molar basis. It would be the sum of the amount of I, and then we have the S2 minus S1 minus R bar natural log of P2I divided by P1I, close paren. Now, just like we had a bar on top of the R, we'll need a bar on top of these S's because it's on a kilomole basis, right? Professor, do I put a bar on the P's? Is there a P-bar concept? Nope, no. Is there a T-bar concept? No, there's no. I mean, if you see T-bar, it's not on a molar basis. It's basically probably somebody's using it to say average temperature. But in this textbook, in this class, we try to reserve the bar on top to distinguish between a mass and a molar basis. All right. All right. Let's say somebody says constant specific heats. All right, how do I change the equation? Well, then the cap S2 minus cap S1 is equal to the sum of the masses, and then I have this term right here. How do I translate from this S naught concept to constant specific heats? Wouldn't that be C sub P natural log of T2 over T1 for the component I? And then minus the R. Well, we've already put it R bar divided by the molar mass of I. Fine, leave it like that. Natural log of P2I divided by P1I. Isn't that the cousin equation when we have constant specific heats? Yeah. So this is temperature dependent properties, temperature dependent specific heat, constant specific heat. All right. So we don't have a partial temperature concept, so this T1I is the temperature initially of that gas And then T2i is the temperature final state of that gas. All right, what about over here? Well, it would be the sum of the amounts times Cp bar of that component, natural log T2i divided by T1i, minus R bar, natural log of P2i divided by P1i. A lot of equations, aren't there? But hopefully they're pretty straightforward. So every now and then I have an error. Do I have an error in any of the equations that you see? Sometimes a student will help correct my error, but they'll do it at the end of class. And it doesn't benefit the whole class. I mean, thank you for finding my error, but it'd be better if you found my error during lecture and let me fix it. Right? I don't think I have any errors here. But if you see something, call it out. You ready to press forward? Okay. Let's solve a problem. So initially we have 0.36 kilomoles of nitrogen at 500 Kelvin and 300 kilopascal in a rigid, well-insulated tank that is connected to a second tank. All right, so I start making an illustration. I have two tanks. Hey, we've solved problems like this before. The second tank is well insulated and it contains 0.14 kilomoles of hydrogen at a different temperature and pressure. A valve is in between. The valve is opened and gases mix and they obtain a final equilibrium state. What does it mean by a final equilibrium state? There's only one temperature and there's only one pressure, right? That's what it means. Determine the final equilibrium temperature, and there it is. And oh, by the way, for the nitrogen and hydrogen, use these values of specific heats. Don't go to tables and try to look up So if you did the first law for the entire system, what's the system look like? Like that. And all it does is shuffle the material inside of it. Some of the hydrogen moves over and mixes, and the nitrogen moves over and mixes. Okay, so you have the first law gives us that the change in internal energy, neglecting changes in kinetic potential energy, equal to the heat that's transferred in during the process minus the work out. What are those? 0. So U2 minus U1 is 0, isn't it? That's our first law. And now how do I calculate that left-hand side? I'll have the mass of the nitrogen, the specific heat, constant volume of the nitrogen, the final temperature minus the initial temperature of the nitrogen, plus the mass of the hydrogen, specific heat, constant volume of the hydrogen, final temperature minus the initial temperature of the hydrogen equal to 0. Only one unknown. T2 is the same. They get to the same equilibrium temperature. So, how do I calculate the mass of the nitrogen? The number of moles of the nitrogen times molar mass of the nitrogen. There's this U2 minus U1, there's two parts of it. One due to the nitrogen, one due to the hydrogen. Why is there a plus right here? Because both of them are part of the system. The system isn't just, let's say, the nitrogen or the hydrogen on one side. The system is both of them together and the contents of both tanks. Yeah. Okay. All right. Now, let's do this. I think I will skip to that. And now, what is the entropy generation during that mixing process? What's that entropy generation? Well, let's go do a second law analysis. So we have the final total entropy of our system minus the the initial total entropy of our system is equal to the entropy transfer. I'm going to write it in like this. If you had any coming in with the heat transfer, I know I could put an integral there, but guess what? That term is 0 anyway because it's well insulated, isn't it? The system is both containers, the contents of both containers, and they're both well insulated. And then, is there any other term in this equation? Entropy generated in the process. Or this textbook uses sigma, and I like to put 1 to 2. So it's entropy generated during the process from 1 to 2. What are they asking us to calculate? Entropy generation. How would we calculate it? By calculating the S2 minus S1. So our answer, sigma 1 to 2, is equal to S2 minus S1. S2 minus S1, I'm going to first consider the nitrogen part and then the hydrogen part. So it'll be let's do the mass, which is the number of moles of the nitrogen times the molar mass of the nitrogen. That's my mass of the nitrogen. Then we're going to have the C sub P of the nitrogen times the natural log of the final temperature of the nitrogen divided by the initial temperature of the nitrogen minus the R. Okay, well, I'm going to replace that by R bar divided by the molar mass of the nitrogen, right? That gives me R for the nitrogen. Natural log of the final pressure of the nitrogen divided by the initial pressure of the nitrogen. And now I have to wrap this equation around, so I'm going to bring it down here and I'll add the number of moles of the hydrogen, the molar mass of the hydrogen, H2. So that gives me the mass of the hydrogen times the specific heat constant pressure of the hydrogen, the natural log, the final temperature of the hydrogen, which, because it's the same as the nitrogen, I'm not putting an additional subscript on T2, right? Okay. Divided by the initial temperature of the hydrogen minus R bar divided by the molar mass of the hydrogen, natural log the final pressure of the hydrogen divided by the initial pressure of the hydrogen. All right, so we just solved for this T2. Remember, there's only one final temperature, and that is 444.6. Okay. The CP is given. The R bar, the molar masses, they're all known. The amount is known. The molar mass are known. Okay. The hard parts are these pressures. Okay. Who wants to help me? I need to calculate 4 pressures. I need to get P1 of the nitrogen, P1 of the hydrogen, P2 of the nitrogen, and P2 of the hydrogen. And all 4 are different pressures, aren't they? Okay, so pressure 1 of the N2, what is it? 300 kPa. Brilliant. Because what started off in that nitrogen tank was pure nitrogen. So it's 100% mole fraction. So the nitrogen, all of it's at that pressure. Okay, so you help me on one. You can't help me on the next one. Yes?
The P1 for the hydrogen is
70 kilopascal. Same logic, isn't it? That I have pure hydrogen in another tank at 70 kilopascal. That's why P1 of the hydrogen is 70 kilopascal. Now a little harder. Who would like to volunteer the strategy to get P2 of the nitrogen? Yes, that's exactly right. So what you're going to need to do is you need to get the final pressure of the mixture, and then once you have that, multiply it by the mole fraction of the nitrogen in the mixture at the end. Now, of these two, probably the mole fraction of the nitrogen at the end, I'm going to put a subscript 2 on there, is easier to calculate, right? So what is that going to be equal to? What's it going to be? So it'll be 0.36 divided by 0.36 plus 0.14. Right? Yeah? Okay. And I forget what that works out to be. I have it right here. Let me look. 72%. 72%. Okay. Now, how do I get the harder part? We got the easy part. How about P2? Ideal gas equation. How about this one? Let me scroll down a little bit. Okay. So if we use the ideal gas equation to get P2, that the final pressure times the total volume of both tanks is equal to the total number of moles in both tanks times the gas constant, the universal gas constant, times the final temperature of the substance in both tanks. Does that help? Yeah. And so the total volume, we have to basically say what is in tank 1 or tank A. Maybe you reserve subscripts 1 and 2 for initial and final state, and then tank A or tank B. Tank A plus the volume in tank B. Okay, so what was the volume in tank A? That's where we had that many kilomoles of nitrogen at that temperature and pressure. That would be the number of moles of the nitrogen times R bar times T1 of the nitrogen divided by P1 of the nitrogen. Just focus on the initial information given about the nitrogen in tank 1. And you can calculate, or tank A, then you can calculate the volume of tank A. Likewise, the number of moles of hydrogen, then R bar, T1 of the hydrogen divided by P1 of the hydrogen. Okay, when I add those up, I think I selected these numbers, 4.988 meter cubed plus 4.988 meter cubed is equal to 9.977 meter cubed. That's the total volume. So that the pressure 2 is equal to total number of moles, R bar, final equilibrium temperature, divided by that volume total. And the final pressure comes in at about 185 kilopascal. Look at our numbers. We started at 370, 185. Okay, it's in the middle. At least it's not over 300, look for an error. Under 70, look for an error. Okay, so when we come up here, this one actually, the partial final equilibrium pressure for nitrogen in a tank is about 133, and then for the hydrogen it comes in at about 51.9. So then you can put in your numbers here and here, here and here. And what do you expect this sigma to be? Greater than 0, equal to 0, or less than 0, negative? Which one? Greater than 0, otherwise our math and our science and techniques are no good. So I think I have it over here. And this Excel spreadsheet, I was going to do it in class, but I ran out of time. But I organized, put the molar mass, put unit descriptions below the label. C sub V, C sub P, number of moles, mole fractions, mass, mass fractions, the initial temperature, initial pressure, the initial volume, add them up to get the total volume, the R. Then one way to do it, I know I did it analytically the other way, but if you've never used goal-seek in Excel, I encourage you to learn it. Once you learn it, you find many uses for it. Where do you find it? Well, go under the Data tab in Excel. In the Data Tools area, select What If Analysis. And then inside this box will show like that. This big red means I copied and pasted and threw it on top. And it'll say, okay, set this cell 07. Usually it highlights, this is O and then 7. So set this cell to 0. You drive that cell to 0 by doing what? By changing, and then you pick a cell. And I pick this cell, M5. And what it'll do is it starts at 400, and then it'll go, okay, how about 420? How about for this, for that? And it'll iterate. It's a root finding, like Newton-Raphson. And if it works, it'll zoom in, and it often does on these simple problems. And it would drive this to 0 and make the final temperature 444.6. So I encourage you to take a look at that. And then I did the entropy calculations likewise. So that's our final entropy value. That's an increase in entropy due to entropy generation of 3.134 kilojoules per Kelvin. Thank you for your attention.